We're going to go ahead and get started with our final final plenary session. I know we got a little bit behind schedule with lunch and the last session, but we want to kind of keep things on time and make sure we have time to check out all the posters that we were hearing about during lunch, and also that we get to hear from our final two plenary speakers. And so we're just going to go ahead and get started. Hopefully people will just be drawn in by our voices to this remaining last part. So it's my pleasure to introduce Pong Ding from UC Berkeley. Take it away.
Actually, I don't know how to use this. Like, okay, thank you. Okay, thank you everybody for coming to this session. Today I'm going to share with you a very recent research project with my student. It's really a fresh paper. If you have any comments, please email us. We are still revising the paper. Okay, it's causal inference in network experiments with the title Regression-Based Analysis and Design-Based Properties. I will explain what do we mean by regression-based analysis and design-based properties. And Meng Sigal is a PhD student from the economics department of Berkeley. Let me first introduce causal inference with network experiments. There are some, I start with notation because I'm a theoretical statistician. And after the notation, I will give you some example. We consider an experiment with units. Sometimes I use I or j to index units from I to n. And there's a network to capture their relationship. The network structure is represented by a matrix with binary entries aij for matrix A. We assume the network is undirected, unweighted, or the edges are binary, and there are no self-links. So the basic notation, and we run experiment, randomize the experiment on those n units. So every unit will receive either treatment or control. Later I will introduce how do we assign the treatment, but generic notation is the di, and the d is the vector. The little d will denote the realized value of the treatment vector. And using our potential outcome notation now, every unit I has many potential outcomes, yi, d, because this d vector can take 2 to the power of n possible values. Now we have 2 to the n potential outcomes. This is a large number, too many of them, and later we will make some assumptions to simplify the problem. Okay, this is the framework. The goal of our study, 2 goals. First, we want to recommend some methods that are easy to implement. So we will focus on regressions. We don't want to recommend anything more complicated than regressions. Least squares will weight the least squares. That's our first goal. Use regression to generate both point estimator and variance estimators. This is the method part. But it does not mean regression methods will all work. Some of them work well, some of them don't. So the second goal is to tell you some theory, or in particular, some robustness theory for the regression-based methods. If the models are correct, regression methods will work. If the models are wrong, do they work? Okay, that's our focus. We will analyze the method without assuming the models are correct. How do we do it? We will use the design-based perspective. I think somebody already introduced this before, but I will recall the definition of design-based perspective. So 2 goals, method and theory. Okay, coming to more concrete setting for network experiment. 2 examples. The first one is a well-known paper in Proceedings of National Academy of Science. It's with the title "Changing Climates of Conflict." It's an experiment on middle school students. Okay, so this is my summary of this network experiment. They have some anti-conflict intervention. The final goal is to encourage students to be engaged in conflict mitigating behavior. So the treatment D vector on unit is a binary treatment, whether they have meetings of anti-conflict colloquium every other week, and outcome Y is measured by self-reporting, wearing some wristband as a reward to be engaged in conflict mitigating behavior. So This is the setting. The original experiment is more complicated than the pure network experiment. Actually, it has two levels. First level is school level intervention. We have treated school and also control school. For the treated school, they randomly assign students to receive this treatment, binary treatment D. For our analysis, we will ignore the school level intervention, just focus on the unit level intervention. And for the network structure, the information from the paper was asking the students, their friends they spend time with in the last few weeks. So based on this survey, they construct a network. And we will use, in our analysis, we will use the 5 largest schools from the data. Okay, it's a part of the data to illustrate our idea. Okay, the second experiment was done by some economists, social networks, and the decision to ensure this is an experiment done in rural China. They want to encourage the farmers to buy weather insurance. At that time, the insurance was new. That's why the farmers didn't know. They want to encourage them to buy with some intensive information session. Also, this experiment has 2 levels. The first level is on the village because there's some price variation on the village level, but we will ignore this level of randomization and focus on the second level on household. For each household, they are either randomized to the first round or the second round, or the intensive session or not. So actually, it's a complicated experiment. 2 levels, the second level has 2 factors to binary intervention. And they also construct the network by asking each household to list 5 close friends. Okay. The question, this is the copy-paste from their paper. They are interested in studying the influence of social network on weather insurance adoption as a mechanism. The reason why I quote this is because in a lot of statistics research, we view interference as a nuisance, but maybe for social science problems, it is a question of interest. Okay, these are the 2 experiments in our mind when we were writing down some abstract symbols. Okay. So third part. What's third part? Oh, design-based perspective on network experiments. So, what is design-based perspective? We follow the 2 papers in the literature, Aaron, Sammy, and also the recent econometrical paper by Leon. Design-based means the following. For maybe some of you are not very familiar with this framework. It's very old-fashioned statistics. Okay, so first we have a lot of fixed quantities in our study. All the potential outcomes are fixed. Okay, like I think nowadays people cite the Neyman-Rubin paper. Actually, in the original paper of Neyman, all the potential outcomes are fixed. Okay, what I did. If you are uncomfortable, just condition on all of them. And we also assume the network structure A is fixed. Okay, because otherwise it's actually a complicated exercise to model it. So fixed potential outcome and a network A. We have to assume something is random. Otherwise, there's nothing for us statisticians to do. Okay, there's a random component, that's D. D is the vector of treatment assignment. Okay, it's the random assignment known and determined by the design. Okay, that's why the whole thing is called design-based perspective. It's driven by the design. Okay, hope you are okay with this framework. There are advantages of this framework. You don't need to model A or Y. There are disadvantages of this framework. For example, people criticize this framework has no external validity. Also, it may miss the dynamics over the network A. But let's isolate the problem first. First, focus on what can we learn by design. The next step is if we are willing to impose more randomness, maybe we can say more. But now only random D. Design-based framework. As I hinted at before, we have to simplify the problem. Otherwise, there are 2 to the power of n potential outcomes. There's no way we can make progress. Okay, the key concept to make progress is to simplify the notation of potential outcomes. This is called exposure mapping by Aaron and Sammy. Also called effective treatment by Maskey. So we're also trying to talk to econometricians. Okay, so what is exposure mapping? It's basically what matters for the potential outcomes. It's a function of the unit I, also a function of D, the treatment vector, and also the whole network structure A. It can be quite general. And we just think the D vector affects the outcome through Ti. Okay. If you assume we have a correct specification of T, then actually you can simplify your notation YID to YIT, and hope if this is useful, T must be much simpler than D and A. Okay, we consider the simple case. T has finite dimension compared with sample size, and T is actually discrete in our study. But you can extend this to more complicated T. Okay. With this T notation, we can define the following quantity, mu I T. If you assume the exposure mapping is correct, you don't need this notation because you can just simply write YID to be YIT. But for mathematical reasons, we want to be more general. So you can have misspecified T. So in that case, this is the quantity you can estimate. What is this quantity? It's the average of all the potential outcome over the conditional distribution of the treatment vector. Okay. If it's too complicated, you can just forget about the notation and think we have a correct exposure mapping. But because we are theoretical statisticians, we want to be more general in theory. Okay. It's nice to be general in theory, but there are prices to pay by allowing for misspecification, because how do you interpret the causal effects if the exposure mappings are misspecified? Also, the definition of mu I T depends on the distribution of T. Then in the future study, maybe the distribution of T is different. So there are challenges in external validity again. It's all about trade-off. You want to do more general math or have external validity. But let's do the theory part. And the causal effects are defined as linear combinations of the mean vector, which first define the mu T quantity. Mu T is the average of the individual quantity we introduced just now. And there's a vector mu of all the levels of T. Generic notation, tau is a contrast of the mu vector. Or you can imagine there are two levels of exposure mapping you care about, just difference between these two labels. Okay, there are examples of exposure mapping. The simplest possible examples. The first one is you just assume T equals D. Like, this is a boring definition because the whole point is studying interference. Now you specify exposure mapping as the original T. But the theory covers it. The second definition is define exposure mapping as whether unit I has friends receiving the treatment. That's trying to measure spillover effect. Maybe a more reasonable definition is this vector. T is a vector of whether I receive the treatment and whether any of my friends receive the treatment. So now we have a 2x2 exposure mapping. This is the factorial exposure mapping. Then we can define, this is classic statistics. So if you have 2x2 factors, you can define direct effect and spillover effect and their interaction. Okay, there are three contrasts you can think about. But anyway, just think about the generic G and focus on estimating this mu vector would be enough. Okay, so as you can see, this is really a complicated problem. I spent 13 minutes on the notation. Okay, it's really, really difficult question because there are so many notations I have to introduce. But I hope the method is clear enough. Okay. So the first one, I want to do some literature review. Not done yet. First review is how do you do estimation? How do you make any progress? The classic estimator is the Horvitz-Thompson estimator. Whenever you want to estimate some mean, you don't have equal probability of observing the outcomes. You have to do inverse probability weighting. Or in this case, we define the probability of the exposure mapping for unit I as pi it. If you want to recover unbiasedly mu t, you do inverse probability weighting. The Horvitz-Thompson estimator you can show is unbiased. Under some conditions, it's consistent, asymptotic normal, and you can estimate the variance. We follow the recent Leon paper, follow their asymptotic analysis, the technical thing. There are assumptions, of course. First assumption is when you define exposure mapping, this exposure mapping should be simple enough. Otherwise, my outcome depends on everybody's treatment. That's too much. So basically, exposure mapping depends on k neighbors, and k does not grow too fast. That's the first assumption. The second assumption is on the pattern of the interference. The interference decrease as the distance increases. Okay, but I don't have formulas for this, but that's intuition. Okay. First one is exposure mapping should be simple. Second, the interference pattern should be simple. Otherwise, there's no hope. Okay. We want to modify this estimator a little bit. It's a very trivial modification. Everybody knows the modification. Modify Howitz-Thompson by Hajek. The difference is you normalize the weights by dividing it by the weighted average of the indicators. Anyway, it's classic in surveys and observational study. There are two motivations, at least in the classic literature. It's more stable in empirical data analysis. The second one is more about logic coherence. Because if you add a constant to your outcome y, you hope your estimator for causal effects should be invariant. But Howitz-Thompson does not satisfy this basic logic restriction. But Hajek satisfies this. This is well known and also discussed by Aaron and Sammy, mentioned by Leon in his footnote, which is a little unfortunate because this is a much better estimator. Why Hajek? There were two motivations I mentioned. There are many other reasons. One reason is, we argue, is actually more natural, at least from the regression-based perspective. First, you can easily show Hajek estimator equals the weighted least squares estimator. You can regress your outcome on a bunch of dummies of the exposure mapping weighted by the inverse of the propensity score. You can recover Hajek exactly. This is a numeric fact. Okay. If you really like regression, this is really natural. But we want to highlight some other advantages of this Hajek formulation. First, it not only gives you point estimator, but also gives you standard error. Because if you run regression, the software package gives you point estimates and also t-statistic or standard errors, the variance estimator. We want to use the regression to generate robust standard errors. But this case is a subtle robust standard error. It's called a network robust standard error to capture the dependence of the data. Point one. Second point, we want to use covariates to improve efficiency in our estimation. And there are many methods you can improve efficiency by using covariates. But if you are running regression, it's really easy because you just plug in the covariates in the regression. Okay. That's the second advantage I want to highlight. The third one is it's easy to implement. We hope somebody else already have this program. Just plug in your data into the program. Okay, that's our motivation. I'm pretty sure the details are difficult later, but let me give you the conclusion in the middle. This is the conclusion. Okay, conclusion, the overview of our results. First, we focus on estimating the mu parameter, the mean parameter, corresponding to the exposure mapping. Second, our recommended method is run weight the least square of the outcome yi on the dummy variables of, on the dummy variable of the treatment indicators. Three choices. First, without covariates. Second, just add covariates. Third, you can actually add dummies and the interaction between the dummies and the covariates, okay, with centered covariates. And make sure you weight your regression by the inverse of the propensity score, the inverse of the probability of the corresponding exposure mapping. Okay, that's our recommended method for estimation. If you want to estimate the variance, use the network robust standard error. Theoretically, the results says, okay, the point estimator, variance estimator works without assuming the linear model is correct. Okay, and the network robust, okay, it works by, in the following sense, the coefficients are consistent for mu, the network robust standard errors can approximate the true standard errors, and covariate adjustment can improve efficiency in many cases. Okay, that's our conclusion. More details. I do want to give you more details about the theory. I think this is the key slide. If you understand this, you understand everything else. Okay, this is a weight to the least squares without covariates. The basic case can give us insight. Recall the vector of exposure mapping Zi, just the vector of the dummies. We run regression of Y on Z with weights. Coefficients of Z equal Hajek estimator. It's consistent asymptotic normal. Moreover, this is the network robust covariance matrix in my mind. This is the only formula for this talk. I know it's too late for formulas, but this is the formula I want to show you. This is the classic sandwich covariance matrix. So we have the bread matrix. It's least squares. W is the weights, the diagonal matrix. The matrix in the middle, the mid matrix, is a little messy. The mid matrix is complicated because we want to capture the dependence of units over the network. Okay, how do we capture it? There is a quadratic form in the middle. It's this residual vector weighted by this kernel matrix K. The kernel matrix is defined as it's a binary kernel matrix. It's actually simple, saying if unit I and j are close enough, you include their product of the residual. Otherwise, you just drop those terms. Okay. So how do you measure whether they're close enough? This is the distance between I and j on this network A. Okay. I have to define the distance on this network, and you have to choose how close is close. There's a parameter Bn to choose. Yeah. There are some formulas for you to choose Bn, but I think maybe in practice you just start from Bn equals 0, 1, 2. You should do some sensitivity checks. Bn equals 0 recovers the classic robust standard error, saying only the residual I matters. Okay, we only have a diagonal matrix in the middle. We don't have any correlation between the units. Okay, hope this makes sense to you. But really, the idea is to capture the network dependence, calculating the distance. Okay? And we hope this V hat Hajek can approximate the true variance. And it does under a lot of assumptions. Okay, the design-based theory shows the following. If you are okay with our assumptions, I didn't show you the assumptions. There are a lot of assumptions. We can show it's asymptotically exact for the true covariance matrix under constant effect. Okay, if there is no heterogeneous treatment effects, it's actually asymptotically exact. Unfortunately, in general, it can even be anti-conservative because the bias, even though it looks like quadratic form, is not necessarily positive because the kernel matrix Kn may not be positive semi-definite, may not be PSD. Okay, that's a problem of this network robust standard error, but it's not a big problem. We can modify it by improving the kernel matrix K by a positive semi-definite kernel matrix by eigen decomposition. If you do eigen decomposition, you will see a lot of negative eigenvalues, but truncate those negative eigenvalues at 0. Okay, and in fact, in our simulation, almost all the estimators, the V hat Hajek, are not positive semi-definite. The kernels, we have to do the truncation to ensure it works well in simulation. Okay, this is the theoretical part for covariance estimation. Okay, more complicated regression with covariates. We regress Yi on Zi, also Xi. Why do we do this? Because Fisher did this in a simple treatment control experiment without interference, runs this away to the least squares. I think I copy-pasted the results because the results are the same asymptotically. Why? Because in the end, what matters is asymptotically is you move this linear part of X to the left. Basically, the theory works for the modified potential outcome because the coefficient of Xi, although it's random, in the limit, it converges to a constant. Okay, so it does not matter in the asymptotic analysis. Of course, there is a finite sample cost. In finite sample, you cannot have arbitrarily many covariates. It can hurt you, actually. But the theory says it's identical to the regression without covariates. And it can potentially improve efficiency. The next one, the fully intacted regression. Why do we do it? Because Winston Lin did it for the treatment control case, and showing including interaction is actually better. It can dominate the naive one, Fisher's and Kova. So we also do this fully intacted version. Also, the results are identical. I copy-paste from the slide before. The only difference is you need to modify the potential outcome as Y minus the corresponding linear combination. Okay. That's the only theoretical game we need to play. Yeah, because in the limit, the random coefficient is actually fixed. Okay. In theory, unfortunately, we cannot show covariate. The regression with covariates can always improve efficiency. No theoretical guarantee. Two reasons. First, the propensity scores are not constant. Second, we have interference. With different propensity scores, even in simple case, we cannot show covariate adjustment improves efficiency. We observed this in cluster experiment before, and with interference is more complicated. There's no guarantee. We have counterexamples in the paper, but we spend a lot of time searching for those counterexamples. They're really dramas, okay? Because in usual data generation process, you cannot find counterexamples. But in theory, you cannot show. That's a difficulty of the theory. Okay, maybe I don't have time for the simulation. Simulation never fail. Okay, it has to work. So I want to tell you the final conclusion. Conclusion is even Hajek estimator without covariate adjustment improves the variance a lot, and covariate adjustment can further reduce variance. And without the adjustment of the kernel matrix, we don't have positive semi-definite variance estimator. It can give you undercovered confidence intervals. If you do this adjustment, at least in simulation, we observe much better coverage. You can see our results in the paper. But I hope the method is simple enough. The method is here. Okay, that's all for my talk.
Thanks. So just one question right now, and then we'll have you back up after Hannah as well. So bringing up this issue of choosing the kernel in the this kind of network robust sandwich, you suggested doing that based on the minimum, the shortest path length between I and J. Are there other choices there that might make sense? A lot of times that could be sort of, is it in some ways a very noisy measure of how much I and J might be dependent on each other, both in their outcomes and in their exposures.
Yeah, I think this part, maybe I hide too much detail here, because this really depends on your definition of exposure mapping. Also depends on how dense the network is. Also depends on the real correlation structure, right? I think there are a lot of subtle issues here. This can change the definition of distance. Also, the key thing is how do we specify Bn, the threshold of distance. I think these are subtle issues. We don't have very good answer from the theoretical perspective. That's why we recommend doing this by varying Bn to see how sensitive is this. Yeah. But I think the key message you want to convey is to use this regression-based covariance matrix. But be careful with this correlation structure. But I don't think we have very good answer to this question. Yeah.
I mean, I think everyone is always happy when a statistician tells them they can just run a regression, right? So, yeah,
that's our goal.
Yeah, awesome. Let's thank Pong. Okay, so our last plenary speaker of the event is Hannah Lee from Columbia. Take it away.
Okay. All right. So let me just start off this talk by saying that I am not a statistician. I am an operations researcher, and traditionally operations research involves a lot of stochastic modeling, optimization, linear programming, convex programming, things like that. So this is actually kind of a strange set of tools to be using on a topic like experimentation, A/B testing. But for the past couple of years, I've actually been applying these tools to experiments to show how we can use these tools to leverage more insights from experiments, especially when there's certain structures behind them. I've done this a couple of times with marketplace experiments and interference, and today I'm going to be talking about some more recent work with a public health intervention. So the motivation, and I do want to say this is joint work with my collaborators, Justin Boutillier, Jonas Jonassen, Uraz Yoeli, and in collaboration with a platform called Kahila. And the motivation, the setting for this platform, Kahila, is tuberculosis. So tuberculosis is a huge infectious disease problem. Every year, there's over 10 million new cases and over 1 million new deaths. And this means that it's the leading cause of infectious disease deaths, second only to COVID in the past couple of years. So this is a huge problem, but it turns out that we actually do have a cure for most of these cases. For most of these cases, there is just an antibiotic that you can take. The problem is that you have to take this antibiotic every single day for 6 to 9 months. So as you can imagine, the adherence is very poor. So this is a map here of the adherence. In many of the countries where tuberculosis is a problem, you have adherence levels of 50, 60, 70%. And there's a lot of reasons for this. There's issues about who can get access to medication, who can keep seeing their doctors during treatment. But there's also a huge behavioral component to this as well. And this is the part that we'll be focusing on today. So Kahila is this platform started by some MIT alumni to help people adhere to their tuberculosis treatment. And in this platform, this was launched in Kenya, in Nairobi in 2016. On this platform, tuberculosis patients would have to log on the app every single day, whether or not they took their medication. And if they skipped a day of taking their medication, then there would actually be a provider on the platform who would call them up and remind them to take their medication. And one thing that I think is just kind of special about Kahila is that on this platform, the providers who are making the calls are actually recovered TB patients themselves. And so they have this extra incentive to help people, and they can also relate with these people better. So maybe that's one way they can help nudge these people to take their medication. So this was launched in 2016 with kind of a smaller scale experiment. I think there was something like 700 people on the platform, 700 people in the control group. And they saw this, and they saw a huge effect size in the number of adverse outcomes. So the people in the treatment group had a way smaller proportion of adverse outcomes at the end of this experiment. So they saw this and they were like, this is fantastic, let's roll this out, let's run a larger experiment, add some more controls, we'll publish, and it's gonna be great, yada, yada. Once they did that though, they actually found that the treatment effects they were estimating in this larger experiment were much smaller than what they found in the initial experiment. And so this is how I kind of got involved. We were just trying to think through this problem about what happened here. Why did we see a larger treatment effect in the smaller experiment and a much smaller effect later on? It turns out there could be a number of different reasons why this happened. Economists have studied this problem, this scale-up problem, and there's a number of different things, but one thing that we think hasn't been sufficiently addressed is the problem of capacity. And so this is what we'll be focusing on in this work. Now, the key issue here is that these interventions are actually capacity-constrained interventions. I said something like, a user will verify every day. As soon as they stop verifying, they'll get a nudge from the platform. That's really not what's happening, actually. It's that a user who stops verifying, once they do that, they'll actually join a queue waiting to be called by someone on the platform. And only when they get to the head of the queue and there's a provider with availability, that provider will reach out to them and call them, give them this nudge. And so really what's happening here is that for each patient, the speed at which they get this phone call depends on how many other patients there are on the platform and the outcomes of these other patients. So this is all one example of interference. This is a SUTVA violation, the fact that one person's outcome depends on another person's treatment assignment or treatment outcome. This violates these statistical assumptions, and this means that oftentimes you'll end up getting biased estimates for the things that you're trying to estimate. In our case, we see that this will, yes, lead to biased estimates, and another implication of this is that it leads to a weird dynamic with power analysis. It actually makes power analysis counterproductive. And just as a little preview of our results, I'll get to how this arises later, but typically in many of these studies, you'll have these interventions, these platforms running a very small-scale experiment to start out with. And they do that, they try to get a sense of how big the effect size could be, and also how much variation there is across users. And they do that to conduct a power analysis to say, how many users do we need to scale out to get, for example, 80% power to detect an effect? And in most of these cases, if you don't have intervention, your power, statistical power, will look something like this, where it's increasing in the number of patients. But in these cases, these service experiments, these capacity-constrained experiments, power analysis could actually look something like this, where it's increasing up to some point, and then after that, it's decreasing. So you can imagine if you're a platform that's trying to demonstrate that your program can be effective, and you think like, oh, let me increase the number of patients without increasing capacity, you could actually be decreasing your power here. Again, this is all because of SUTVA violations. There is so the structure that I'm talking about here, the kind of like structure behind this problem, it is related to some work on marketplace interference, specifically because there's capacity constraints. But the structure of interference is actually a little bit different than the typical competition-induced interference. Here, just strictly capacity-induced, but it is related to some of that. I worked on some of this in the past, studying these things with stochastic models. We'll end up doing that here in this problem as well. And I will say another very related paper to this is the paper called Experimenting Under Stochastic Congestion, Schwanging's paper. It's great. You guys should all go read it. They also look at kind of this, congestion, capacity-constrained queuing, what's essentially a queuing system, but we focus on very different estimands and kind of effects. All right. So one thing I want everyone to notice about this is that, yes, we have these SUTVA violations, and typically what that means is you'll get biased estimates. Well, what do we do from there? Do we just stop? Do we just, give up? We're like, okay, can't estimate anything. No, that's not really what we're going to do. We noticed that in this problem, there's actually a very structured kind of interference. These patients are really operating according to this kind of queue, and if you're familiar with operations research, well, you know that queuing theory is like half of this field. People have studied this for a long time. Given that we know this much about queues, shouldn't we be able to say something more about this? And so essentially, that's what I'm going to be doing here. Oops. Okay. So I'm going to build a stochastic model that describes how these patients are acting. So first, we say they're either NT, patients in treatment, and NC, patients in control, and that patients can be in two different states. They're either in their verified state, which is they're taking their medication, or they're in the non-verified state. They've stopped taking their medication. And we say that we have M providers on a platform. So people in the control group, they don't get access to this provider support calls. And so they'll just transition between these two states of their own accord. So people who are verified can stop taking their medication at rate lambda, and they can start taking their medication at rate tau. This is pretty simple to analyze. People in the treatment group actually follow a much more complex dynamic. So here, people, if they're verifying, they can again stop taking their medication at the same rate lambda. But once they do that, they really end up joining this queuing system. They end up joining this queue, and when they're at the head of the queue, they get a nudge from a provider on the platform. We say that these providers, there are M providers, and each one can make calls at rate mu, and every one of these calls has some probability P of being effective. So P is not necessarily equal to 1. You can't make a patient do anything. It's probably just some kind of nudge. But even if a patient's not called, they can still start taking the medication of their own accord, just like the control patients. And so there's also this probability here, this rate tau here of abandoning the queue. And so in this treatment group, people in the verified state, they're in the good state, and everyone in this queuing system, they're in a bad state. Okay. Now, the outcome of interest that we'll focus on today is adherence. So this is just the proportion of time you spend in the good state, in the verified state. And so for control patients, we can define a random variable, just some variable x that depends on the user. For treatment patients, though, this random variable really does depend on the number of patients and the number of providers in the platform. And then we focus on the steady state adherence level. So what is the expected value of these quantities in like kind of a long run setting? For control patients, this is very easy to quantify using just the parameters we saw before. For treatment patients, it turns out that the proportion of time they spend verified is this 1 minus the expected length of the queue. Sorry, that should be normalized by n. And so this is a function of m and n. Oops. Now, what does it mean to experiment on the system? What quantities do we care about with experimentation? The global average treatment effect that we care about for n providers and n patients, we define this to be some theta. And note that, again, this has to depend on m and n. An estimator is just, the naive estimator that we consider is just the difference between the time average of the treatment group and the control group in terms of their adherence levels. And then we look at the expected, expectation of the estimator that we've defined. The expected value is, again, just this function of this m and nt, the number of patients in treatment, minus the control quantity there. And I will say that we can actually characterize all of these quantities. Like we have solutions for them. They're kind of complicated. They're all in terms of these steady state quantities. It ends up just being really hairy and not really a good way to get analytical results. And so in order to actually make progress with analytical results here and things that are interpretable, we end up taking what is called a mean field limit and a diffusion limit. With a mean field limit, you can think of this as kind of an analog of the law of large numbers, but for these like stochastic systems. And this allows you to approximate the average effects. And a diffusion limit, you can think of this as kind of an analogous to the central limit theorem with this root n scaling. This will allow us to approximate the variance of these different quantities. Okay, so once we define all that, what does this actually say about our intervention at hand? The first implication that we see is that the more patients you have, the smaller the effect size. And we actually find that the effect size looks something like this, where as you're increasing the number of patients for a fixed number of providers, the effect size will go down. And we are able to prove this. We're able to both, so we're able to prove this. We can characterize exactly what the effect size is. And this is pretty natural. The more, for a fixed capacity, if you increase the number of patients need to wait longer in order to be called. And so they're spending more of their time in this bad state. And so I think this is a pretty natural result. Another thing that we can see is that if we increase the number of providers, then the effect size will be increasing. Again, this is pretty natural. Now these patients will be called faster than they were before. And so they're essentially getting more treatment. And this is something that we prove as well, that conditioned on a fixed n, fixed number of patients, as you increase the number of providers, the effect size will be increasing. And so this is kind of saying that, one thing that this is highlighting is that really this treatment is dependent on n and m, and n and m together kind of define, what dose of this treatment are you getting? Where for larger capacity, smaller patients are getting more treatment in some sense. I also want to point out that this decrease is nonlinear, so it is not just decreasing with n. And in particular, there's actually this flat portion at the very top where the effect size is not decreasing at all. So there, for a fixed number of providers, you can kind of increase the number of patients for free and not have any negative effect on your effect size. And the reason for that is, this gets back to the queuing theory part of this. The reason for that is that in these smaller n regimes, in expectation, most users who come to the queue will get 0 wait time. They'll come to the queue and there will be someone available to serve them. And so because of that, they're still getting served immediately, and there's kind of like some number of patients that you can support doing this. And then after that, you actually see this effect size decreasing much steeper, and it's actually decreasing with 1/n. This is something you can prove as well using queuing theory results. Okay, so everything I'm going to say will follow from the previous slide pretty much. Here, another thing that we note is that capacity must be scaled appropriately when you're thinking about scaling out these interventions. Just as a simple example, suppose that the platform runs an experiment where they have 200 people in the treatment group, but they want to scale out to 1,000 people. And suppose that they don't know that this capacity issue is a thing, and so they just naively keep the same capacity on the platform. That will then lead to essentially biased estimates, where, let's see, for 1,000 patients, you have this lower effect size there of about 0.12 or so. But if you run an experiment with 200 patients, you're going to see this effect size of over 0.6. And so that difference there is this bias, and this can clearly be pretty large. So this results in biased estimates. I put bias in quotations here because it's kind of a strange type of bias. It's bias because you might not be careful in defining exactly what intervention you're thinking about. Like, this intervention is really a function of m and n. Your estimand is a function of m and n, and so is your estimator, and you just really have to be careful that you're thinking about this appropriately. All right. Another implication of all of this is that when you're thinking about how platforms do power analysis, we actually find that this is now counterproductive. So this is getting back to what we were saying in that one of the earlier slides. So here, power is defined as the, given that you have an effect, the likelihood that you can actually detect this. This is an increasing quantity in basically the effect size over the variance. And the larger that this quantity is, the more power that you have in your experiment. If you don't have any interference, then if you don't have any interference, then the effect size will be constant in the number of patients, but the denominator, the variance, will actually be decreasing in the number of patients. And so as you increase the number of patients in your trial, your power then goes to 1. So you end up with that pink line there. But in these service experiments, these capacity-constrained experiments, now what increasing the number of patients does is you're decreasing your variance, but you're also decreasing your effect size in the numerator. And so because of that, your numerator is decreasing, your denominator is decreasing, and so power, could be increasing, could be decreasing. It's unclear. It's unclear a priori, but we actually find that it looks something like this, where it's increasing to some points, and then after that, it's decreasing. Again, this is a place where queuing theory can come in handy. This is that point where that kind of like a power optimal point. It's not random. It turns out this actually corresponds to what's called in queuing theory as the quality efficient driven regime. And you can solve for this in terms of m and n, your different parameters. Yeah, so going back to the experiment setting, well, now if we say that we want to be well powered to detect this effect, we can see that with 2 providers, no matter how many patients you include in your sample, you're never going to have 80% power in your study. What can you do then? You can increase the number of providers, and this will actually, allow you to have better power, assuming the right number of patients in there. And again, you can quantify this kind of like right number as maybe the QED regime in queuing theory. So all this to say that in order to maximize power, you need a joint power and capacity analysis in these study designs. Another point, though, is that you don't always want to be maximizing power necessarily, and it really depends on what the point of your trial is. And there's kind of two types of trials I'm thinking about here. There's an efficacy trial and an effectiveness trial. And in an efficacy trial, these are kind of standard terms in these healthcare settings. What you want to show is that in the ideal setting, your intervention can have some positive effect. And so in that case, this is kind of like an early round experiment. In that case, you might want to be maximizing power in your experiments. But in an effectiveness trial, this is trying to get at, in standard, in the expected conditions and real world conditions, how good is your intervention? And so here, you might want to run an experiment where you do really model what kinds of effects you'd see in real life. Okay, and finally, I want to talk about a couple of related settings where this issue also comes up, because we realize this issue working with Kahila on this tuberculosis platform, but it's really quite a general phenomenon, and it shows up in a lot of different scenarios. So one scenario where it shows up is this clinical trial called the HeartStrong trial. This was a very similar structure for heart attack patients. They needed to take their medication, and this intervention was designed to help them adhere to their medication by giving them electronic pill bottles. So this would track whether or not they opened their pill bottles and took their medications every day. And if they didn't, again, someone on the platform would reach out and call them. So I think this was like a 1,500 person trial. I think it was about a year. It was like it had a huge budget. There were a couple of other effects, or a couple of other parts of this intervention as well, with social support. Basically, everyone expected this to work. And everyone really, really thought that this should have worked. But at the end of the study, what they found was no effect. And so, why is that? Well, 2 years later, the same authors of this study came up with a follow-up study where they said that they looked at different patients in the trial and they saw heterogeneous wait times and how long the patients needed to wait before they were called after they stopped taking their medication. And that for the people who didn't have to wait very long, they actually did see a positive effect. And so again, this is just another setting where we see the same phenomenon happening. And we've looked at their supplementary materials. We look at how they plan their study. They mention a power analysis, but no mention of how to scale up capacity. And so yeah, again, you really do need to consider this. And not trying to hate on this one setting in particular, I'm just saying this is a very common thing. This is also something we've seen in other scenarios. One of them is Noom. This is a weight loss app where you log your food every day. If you don't log, someone might text you or something. We've looked at their supplementary materials, and they also talk about this. They also have a capacity-constrained intervention, but they don't talk about anything at all about capacity in their power analysis. They only talk about the number of patients. They still end up finding a positive effect, so it's fine, it all worked out for them. But in other settings that might not have, you can think of similar settings happening in marketplaces, in call centers or help desk. You might see a similar phenomenon. You can also think of this as probably something that would likely happen in education settings. This is also a very natural model for students. Students could go back and forth between the states of understanding and not understanding something. And when they're not understanding, they need a patient to nudge them back into understanding. And so the teachers are kind of the capacity constrained service here. So just really, this is a very general phenomenon that happens in many settings. And to wrap up, in this setting, we talk about this healthcare service intervention where we see that there's interference caused by capacity constraints. And because of this, we see that effect size is decreasing the number of patients. Power analysis can actually lead to worse power in your experiments. And you really do need to be considering the capacity constraints of your system when you're thinking about running these experiments or scaling up your interventions. And at a higher level, I just want to say that a lot of these insights that we got from the experimentation was by applying these typically operations research queuing theory models to experimentation and leveraging the underlying structure from these interventions to get more insights on the experimentation side. So this is all a work in progress. We'll hopefully have a paper out soon. If you want the paper, feel free to email me and I'll send it when we have it out. Cool. Thank you.
Yeah, this was great. Very, very interesting. Pong, if you want to join us on stage, we'll take some questions for both of you. But first, I wanted to ask a question of you, Hannah. Just if I'm following correctly, one of the implications here would be also about the type of subjects that you might be recruiting into the experiment. So normally we might think one way you could increase your power is if you have, you could have a population with very high adherence already. You're going to have ceiling effects. You can't do much. So you might say, oh, we really want to recruit a larger fraction of patients with low adherence, and that will increase power. But if I'm following correctly, some of your results might suggest that they're going to make for longer queues, even with a fixed number of patients. Is that kind of the intuition to have there?
Exactly. Yeah, that would lead to longer queues. So potentially, it's unclear there because you have one effect that would push that to having a higher effect, and another kind of dynamic that would push it to have a lower effect. So it's unclear exactly what would happen in that setting. Yeah, but it could be higher or lower.
But I guess maybe that sort of points out why it is then nice to actually use some kind of structural model to clarify which one of those things is going to dominate in some particular case.
Exactly.
So I think we've got Harang has a mic, and so if there's some questions in the audience.
I have a question for Hannah. If you fix the I'm over here to your right. If you fix the ratio of n and m to some constant, would you find that some of this kind of goes away?
Yeah. So one thing that you would want to do is potentially fix the ratio. You do have to allow for some kind of extra buffer room just to account for variability because of randomness. And in the queuing theory way, they call this the square root n staffing rule. And so you can follow things like that. But yeah, you do. That's kind of like a second order term, but primarily you do want to make sure that you're scaling up the proportion.
And as a direct follow-up, as a consequence, is there an optimum ratio where you hit that flat point where the expected queue length is 1 or whatever that minimizes the wait time?
Yes, exactly. So it depends on optimal with respect to what. If you're talking about optimal with respect to power, then there is kind of that peak, and that peak is exactly that square root n staffing rule, this QED queuing regime.
Cool. I think we have another question over here.
Yeah, so my question is also for Hannah. I wonder whether you have considered correlations between the likelihood of adherence and the treatment effect of the nudge. So my idea is that people who are less likely to adhere to take the drug are also less likely to be nudged by the treatment, by the call. Have you ever considered the correlations between the two?
So you're saying the providers on the system might call them less if they know? Okay. Yeah. So yeah, it sounds like you're asking about the difference between someone's base rate of adherence and then what the lift in their adherence level after a call. So actually, yeah, my co-authors did some work on this in a prior paper, and they actually found the opposite, that they could identify high-risk patients. These high-risk patients typically are less likely to adhere themselves, but on these high-risk patients, a call actually has a larger effect. And for a low-risk patient, well, maybe they're already adhering, there's just not much room to grow, kind of getting back to Dean's original question. And so you actually can target the patients that way. So if you are capacity constrained and you can't increase the number of providers, maybe that's one way where you could actually increase your treatment effect.
And I wonder, related to this idea of maybe some room for these kind of additional heterogeneity, whether you consider the idea that actually if I don't get a call quickly, if I'm stuck in the queue in treatment, I could actually sort of have a slower rate of returning to the good state than in control, right? Maybe you told me people are going to call me if things are bad. No one's calling me. I guess I'll just stay in the bad state.
That's
right?
true, yeah.
So, and that could further exacerbate this kind of process in an even more extreme way, I suppose.
Yeah, and I suppose in that case, you might actually see a negative treatment effect if the queue is long enough. Yeah.
Yeah. Cool. Question here.
Thank you both for the wonderful talks. I had a question for Peng. It is related to the question Dean asked earlier. When you talked about the kernel and you said that you can have some negative eigenvalues and you have to truncate it, I was trying to understand a bit more. Is that because like the choice of the kernel is not appropriate, or is it a problem with the regression itself? Like if one is getting negative eigenvalues, what does that tell us really about what's going wrong in some sense?
Yeah, I think there are many choices of kernel. Actually, we found and testing our simulation, the uniform kernel works the best. It looks very naive, but it works the best in the simulation. It may not be positive, definitely just because of maybe the network structure is kind of weird in some way. Yeah, it's well known in the spatial econometrics literature. There's a version called spatial robust standard error. They encounter the issue, but we found in network setting it's more severe. Like it happens almost all the time. The kernel is not positive, semi-definite. Yeah.
Just while we're getting into the meat of this sandwich, I thought that one of the issues with some of these kind of network robust variance estimators, et cetera, is that they require like multiplying a lot of residuals together, right? And so this is some kind of like might consider order n squared residuals. Okay, maybe with this kernel, it's less than that. Is there anything we can do about that? So I just maybe naively, I don't know, in a paper, I decided to compute this by using a sampling scheme to try to compute this network robust standard errors. Do you anticipate some way that we could do something like this if you're sort of functioning at the scale that a lot of our attendees are?
Again, in the most ideal case, if you can cluster your units on the network and there are enough clusters, maybe you just use the cluster robust standard error, right? But maybe this network version can allow for some complexity. Maybe you cannot easily cluster them. Yeah, I think it's a difficult question. It really depends on how do you specify your exposure mapping, how dense the network is, and depends on many things. It's a very subtle issue to implement. That's why we can only recommend, there's a formula you can apply, but make sure you do all the sensitivity checks near the choice of that threshold. There's no, it's like in the non-parametric statistics literature, there are a lot of theoretical discussion, or you choose bandwidth in this way and that way, and people do simulation and none of them worked. And the real practical way to do the analysis is to vary the parameter. Yeah.
And so maybe part of just the request there is that you're trying to make things simple, telling us to use regression, et cetera, is to make it, make sure we can make it scalable as well. I think we have another question over here.
This is for Hannah. So while we are calculating the power, I noticed that you probably were considering all providers to have the same, let's say, power to nudge or efficiency in nudging. So let's say, given these are humans and different, so is the difference in their, success of nudging being already taken into account when you calculate P overall, or does your work consider that all providers work the same way? And I ask that because that will have some form of impact on the power calculation eventually, right? Especially because when you have proposed that increasing the number of providers does get us to a higher power. So
yeah, that's definitely true. So in our work, all of these plots you saw were like calibrated to the data. When we do that, we assume that there's just one P for all of the providers, but you could very easily incorporate a wide variety of different probability of the effect working, and you could still see you could still like analyze that with the model, and you'd see very similar results in terms of n increasing or m increasing. I think the one place where that would be an issue, this isn't actually an issue that people have, that economists have pointed out with scaling up these certain types of interventions like this, that when they're running these small scale studies, they can hire really good teachers or really good whatever you're looking for. And like their probability that P would be really, really high. but once you have to scale this up to a larger proportion of people, maybe you can't find that many amazing teachers so that people go down. And so if you do that, then that would actually change some of the dynamics, like orthogonal to the dynamics we've talked about today.
Cool.
I've got a question here. Question for Hannah. So you already made a connection in the last slide to marketplaces, customer support, and maybe content moderation. So connecting that to the talk you gave earlier in the parallel session with regards to experiments, how do you see that work that you've done here being extended to experiments in content quality moderation and customer support?
Yeah, so I think you would find very similar effects here. As long as you have some sort of capacity constrained service that you're trying to experiment with, whether that's content moderators or people at a help desk dealing with tickets, actually having to deal with customers, like you'll see very similar effects there as well.
Cool, thank you.
Yeah, and over here, yeah.
Yep. Hello, this is a question for Peng. I was wondering, especially since you're focused on this counterfactual expectation under a particular exposure mapping estimate, is there a way to represent somewhat more standard estimands like the average direct effect or average indirect effect in a similar regression type structure? And second question that is somewhat distinct is, because you wrote down this variance estimation formula that has the square kernel, which if your network structure is actually like some mutually exclusive clusters, it collapses into cluster standard errors, presumably, right? Is there some way to think about, this is somewhat ill-formed, but is there some way to interpolate between cluster robust inference and network inference that you can attack with the formulation that you've written down?
Okay, so there are two questions. First one is, there are other definitions of direct spillover or that type of effects. Can we use the regression formulation to estimate those parameters? I think the answer is yes. If you define those effects in terms of exposure mapping, yeah, I think that's a key concept there. Yeah, I think the answer is yes. Well, ideally, we hope at least in my mind, I hope all the estimators can be formulated in terms of regression, because at Berkeley I teach two courses: causal inference and linear regression. So I try to write all estimators in terms of linear regression. And the second question is the interpolation between cluster robust standard error and network robust standard error. Right? I think network is the more general version. Cluster is a special case. But from my reading of the literature, like some econometrics paper claim, at least when they do clustering on network, they only have a very few number of clusters. In those cases, I don't know how to apply the theory, at least the cluster robust standard error. Yeah. I think I don't know the answer. It's a very subtle issue.
Oh, and we've got a question over here.
Hi, yeah. This question is for Hannah. Great talk. I'm curious whether you can get some kind of empirical or experimental quantification of this bias by, for example, like conditioning on people having low wait times in your experiment, or even like randomly bumping people up to the front of the queue and then seeing whether the treatment effect for those people is larger.
Yeah, I think you could definitely do something like that. I think, again, it also depends on being very precise about what is the estimand that you're trying to measure. So, for example, one thing that you're trying to measure is the probability of a call working, conditioned on the person being called the very next day, for example. Then you could look at just the subset of people that, by chance, happen to be served very quickly. But I would say that in any actual implementation of this, you would have the queuing structure in the background underlying this. And so you couldn't just like take the treatment effect on the people who are called in 1 day versus 2 days and 3 days and just average them. You would still have to account for these queuing dynamics in there.
And I think maybe a kind of a question related to both of these talks and say using the queuing model, thinking about what are some of the good roles for a kind of structural model of the data generating process in this, right? Like we want to run a regression, but maybe we want to think about the underlying process. And I think, Hannah, also in what you were talking about, right? In the end, maybe still we want to compute a difference in means. And so how do you both think about kind of the value of these sort of stochastic process or structural models in planning and analyzing experiments?
Maybe Hannah, go first.
Sure. Yeah, so I clearly think it's useful because I keep doing it, but I do think it's complicated in terms of like when is it useful and what is it useful for. So like using this, we can get insights like this queuing stuff here. We've applied this like similar stochastic modeling to like marketplace experimentation and find insights there, like when is bias large or small depending on supply and demand imbalance. But I do think there's like one issue that we keep coming up to that's like, it's hard to go from this structural model to like, hey, if you actually have data, what do you do with that data? Because in some of these models, well, it's like, yeah, you kind of need to like fit the model to the data. There's a bunch of choices to be made there. There's all these like other things that you have to take into account as well. And so it's not like I could have, like some of the marketplace papers, I could have immediately given it to a platform and be like, implement this. Like there's still like other layers that you have to build on top of the initial structural modeling.
But I guess maybe in some ways that's an advantage of using these models more in like a stylized way in the design phase, is that maybe they provide some helpful guidance, even if you tried to fit them to the data, they would be completely rejected by the actual data.
Yeah, I do. I think like here in this example, it's like in the design phase, like this gives very natural insight that you can actually implement. Maybe it becomes a little bit harder in like the post-analysis or post-experiment like analysis phase. But it really depends. It really depends on the structure and the exact like question that you're talking about.
Yeah, Pong, how do you think about this?
You have a very complex feeling about the role of models because like from the theoretical part, we have the so-called design-based framework, and actually the literature of spillover or interference originally is more like model-based perspective, like econometricians run linear means model and a lot of other models, and some statisticians think, oh, what are you estimating if the model is wrong? And actually in this spillover case, the design-based framework kind of win, like the Aaron and Sammy paper just told us, actually this is a great advantage of design-based framework. It's like free you from modeling the outcome process and the network. But I think now I'm more in the middle, saying what's the role of model? I have to think about the model, because if the model is correct, you can have optimal inference. But at the same time, we use the design-based framework to evaluate the property of the estimators, allowing for the misspecification of the models. So I think we should do both and hope these two things will agree with each other. I remember when I was a student, I took Carl Morris' mathematical statistics course. He always advocate we should do statistics from both Bayesian and frequentist perspective, and hope the method we recommend has justification from both sides. So I think it's the same for this interference world. If we propose some method only works for our design-based world, actually it's a little strange.
Yeah, I definitely agree with that. Like more work from both sides on these things.
And I think that kind of ecumenical perspective is maybe a good way to wrap up some of our programs. So let's thank both of our speakers.